So in the previous part of this video lecture, I asked this question, which is just checking that you understand the definition of Q in this equation for the E field inside a parallel plate capacitor. And if you look back at how I defined it, I said that we have a charge Q on one plate and a charge negative Q on the other plate. And so if Q is 1 nanocoulomb, then we have plus 1 nanocoulomb on one plate and minus 1 nanocoulomb on the other. To summarize some of this, let's look at what happens when we release an electron between two parallel plates. And there are actually many technological applications where this sort of thing happens, where perhaps you're accelerating an electron beam. So we're going to start with this electron halfway between these plates. I've given you the plate separation, the area of the plates, and the charge on the plates. And we now know that the E field inside there is going to be Q over epsilon naught A. And that's it. And now remember that we have that the E field is the electric force over the Q probe. Well, you know, this electron in here is responding to this field. We can think of it as a probe charge. And so the force on the electron is just Q probe, which is negative E, right? One negative fundamental charge times the E field. And the E field is just this magnitude to the right. And finally, if we wanted to know, say, the acceleration of that electron, all we have to do is this. And so the acceleration is going to be negative E over m. And you could now, if you want, go ahead, plug this charge, this area, this epsilon naught, which I gave in a previous slide, and the fundamental charge in here and get the acceleration on that electron. Finish up, let me just talk briefly about a conductor in equilibrium and what the E fields are like in and around it. And let me clarify what equilibrium means here. It means that the charges in this conductor are not moving around. So think about what would happen if there was an E field inside the conductor. Well, that would mean that electrons, which are free to move around inside the conductor, would be accelerated by that E field. But we've just said this conductor is in equilibrium, and so the charges must be static. If there was a non-zero E field inside it, they wouldn't be static. And so we can conclude that the E field is zero inside a conductor in equilibrium. Similarly, if there was an E field at the surface and it pointed at some angle, then any charges on the surface would be accelerated along the surface, and that would also violate equilibrium. So while there might be an E field at the surface, it must be perpendicular to the surface.